Okay, welcome back to the calculus class, and here is the slide. And okay, so before we go to the next part, so let me just explain one more time regarding this concave upward or concave downward. Okay, so when I say concave upward, then that is defined by the following, the relative position, I guess. I mean, so if the graph of the curve is above the tangents on certain interval, then we say the function is concave upward, and that happens f double prime is positive. Okay, concave downward, we say the graph or function is concave downward if curve is below the tangents, and that happens when f double prime is negative. So this concave downward or concave upward is not related with increasing or decreasing of a function. So concave upward or downward is not is not related with increasing or decreasing. Okay, so these two are the definitions, and here is one note. So your function can be increasing and concave upward, and can be increasing and concave downward, and decreasing and concave upward, and decreasing and concave downward. So if your function is increasing and concave upward, then the shape is similar to the right hand side of x squared function. It increases like this. But if your function is increasing and concave downward, it increases as in negative x squared function. If your function is decreasing and concave upward, the shape is that of the x squared function. It decreases and concave upward. And if your function is decreasing and concave downward, then your function decreases as in negative x squared function. Okay. So please remember that y equals x squared, the function increase, decreases, and increases like this. And negative x squared, the function increases and decreases like this. So here is the first pattern, and then here is the second pattern, then third pattern, and then fourth pattern. So that's why I try to remember these two functions, x squared and negative x squared. Those are very simple, intuitive, but it will be helpful to identify the pattern of the graph. Yes, so I already explained these topics. So the concavity test, if I tell you one more time, says the following two statements. First, if your f double prime is positive, then your graph is concave upward. That means the shape will be like this, decreasing or increasing. If your f double prime is negative, then your f is concave downward, meaning your function increases like this and decreases like this. Of course, you may consider the relative position between the tangents. Oops. Okay. So these two cases are concave upward because the actual graphs are above the tangents. Then below two graphs are concave downward case because the actual graphs are located to the, I mean, located below the tangents. Now, a point on a curve y equals f of x is called an inflection point. Actually, this inflection point is used quite often these days in many newspapers, but they are not using the mathematical definition. In mathematics, when I say an inflection point, that means your f is continuous and and curve changes from concave upward to concave downward, or concave downward to concave upward. Then, I mean, at certain point, then that point is called an inflection point. So, if so, f double. So, in other words, if f double prime changes the sign, okay, at p, then this p is called an inflection point. I mean, to the left of, so a more accurate expression is this: the sign of f double prime to the left, p is different from the sign of f double prime to the, oops, to the right of p. Then we say this p is called an inflection point. Okay, so let me go back to the figure we used, this. So here, given this B point, to the left of B, concave downward. To the right, we have concave upward. So B is an inflection point. Then how about C? To the left, concave upward. To the right, concave downward. So C is another inflection point. And D, to the left, concave downward, and to the right, concave upward. So B, C, D are all inflection points. However, in case of E, to the left, concave upward, to the right, concave upward as well. So E is not an inflection point. In case of P, to the left, concave upward, and to the right, concave downward. So P is another inflection point. And since the function is defined between A and Q only, A and Q are not inflection points, and we have these four inflection points. Okay, so we have four inflection points in this graph. So if the concavity, okay, is different to the left and to the right, then given point is called the inflection point. And please note that in case of E, to the left and to the right, the curves are concave upward. So E is not an inflection point. So this is the definition of the inflection point in mathematics. So when you read the newspapers and if somebody say inflection point, that is different from our definition. Oops. Okay. And now we have the following second derivative test. Suppose that f double prime is continuous near C and f prime of C is 0, then we have one of four patterns. You may have local minimum, local maximum, or just purely increasing or purely decreasing function, right? But it has a slope, the horizontal tangents. So if f prime of C is 0, then you have these two, one of these four situations. Now, if f double prime at C is positive, that means, what does that mean? Your f prime, f, f double prime C is positive. So in that case, you get concave upward locally. So you have this situation. If f prime of C is 0 and concave upward. So the first situation. So we will have a local minimum there. If f prime of C is negative, I mean, if prime C is 0 and f double prime C is 0, then that means your function is concave downward. Then the shape will be that of negative x squared, like this. So your function will have concave local maximum there. So here is the situation for concave downward. And here is the situation for concave upward. And please remember, f double prime SC is positive. That means your function is concave upward. So this is the second derivative test. And this test is quite useful. I mean, it can be extended to multivariate case as well. So if you read some optimization textbook, then some generalized version of the second derivative test is used in many optimization theory. So if you came from some departments and if your research considers certain optimization, okay, say in the operation research, the research, something like that, then you need to be familiar with the second derivative test. This is quite intuitive if you look at this graph. And for calculus class, it may look simple, but it is quite useful. It can be extended to multivariate situation as well, some vector situation. I mean, so let us consider the following example. So discuss the curve with respect to concavity, points of inflection, and local maxima and local minima. And so I may give you some problem like this. Okay. I like some problem as in example 6. I may ask you the concavity, points of inflection, local maxima, and so on. Okay. So in case of concavity, concavity depends on the sign of f double prime. So in order to answer this concavity, I need to find f double prime. So if the right hand side is denoted by f of x, I can find f of prime and f double prime. So f double prime is 12x times x minus 2. So I need to check, I need to find the intervals where this f double prime is positive, then those on those intervals your function will be concave upward. If I find the intervals where f double prime is negative, then your function will be concave downward. If I want to find points of inflection, I want to find the points where f double prime changes the sign. So to answer the second part, the points of inflection, I need to identify the concavity of this function on the intervals. And the intervals are obtained by considering the points where f double prime is 0. F double prime 12x times x minus 2. That is 0 when x is 0 or 2. So as we did previously, given these 2 points, the interval is split into 3 points, 3 intervals. To the left of 0, between 0 and 2, and to the right of 2. Now to the left of 0, 12x is negative, x minus 2 is negative, right? 12x is negative, and x minus 2 is negative. So if you multiply them, f double prime is positive because minus times minus will be plus. Between 0 and 2, 12x is positive, but x minus 2 is still negative. So f double prime is negative. And so you get between 0 and 2, your function is concave downward. And between to the left of 0, your function is concave upward. And to the right of 2, 12x is positive, and x minus 2 is positive. So f double prime is positive. So your graph is concave upward. So I could identify the concavity right? So it is concave upward, concave downward, and then concave upward again. Now, how many points of inflection do I have? Two, because the sign changes at 0 and 2. So 0 and 2 are inflection points, right? Now, what is the third question? We want to find the local maxima and local minima. In order to find the local maxima and local minima, I need to find the points where f prime is 0. Now please remember, f prime is this one. That is 0 when x is 0 or 3. Okay. Now at 0 and 3. 3 is here. Okay. So 3 is simple. What does this test say? F prime is 0 and f double prime is positive, then you get a local minimum, right? And f prime is 0, but f double prime is negative, then you get a local maximum. So in case of C, in case of 3, f prime is 0 and f double prime is positive, concave upward. So you get a local minimum. So at 3, you get a local minimum. Then what happens at 0? The theorem does not tell you. Okay, so the previous theorem tells you that if f prime is 0 and f double prime is either positive or negative, then we can tell, right? I mean, you will have local maximum or local minimum. The problem here is that f prime at 0 is 0 and f double prime at 0 is also 0. Then what I have then in that case people usually consider the graph of a function. You remember what I did in the previous example? Given f prime, I could find some general shape of the graph, right? So f prime is 0 when x is 0 or 3. So the real line is split into 3 pieces as well. Now to the left of 0, f prime is positive. Is it positive or is it negative? To the left, 4x squared. 4x squared, this is always non-negative for any x value. Because it is x squared. Okay, so let me rewrite this. So 4x squared, this term is positive, 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 regardless of the x value. And then how about x minus 3? To the left of 3, it is negative. To the right, it is positive. Then f prime is the product of these two signs. So f prime will be negative, negative, and positive. So that means my graph is decreasing up to 3 and then increasing beyond the 3. Right? So this will be the shape of the graph. Okay. So at 0, do I have a local minimum or local maximum? No, because your function is just decreasing, right? Now, before we go to the next part, can I combine the information obtained from this with the information obtained from here? If I consider the graph on the left based on f prime, I could tell only the increasing or decreasing pattern of f. Now, when I look at the one on the right inside the circle, a blue circle, I have the information about the concavity. Okay, so here is the idea. So my function decreases up to 3. Okay, up to 3, my function is decreasing, but up to 0, it is concave upward. If it is concave upward, so here is 3. So my function decreases up to 3, but up to 0, it is concave upward. So probably it will decrease as in y equals x squared pattern. Between 0 and 2, f prime is still negative, so that the function is decreasing, but concavity is concave downward. So the decreasing pattern will be similar to that of negative x squared function. And then between 2 and 3, my function decreases, but concavity is concave upward. So we have this. As we observed, we have 2 inflection points where this concavity changes. Okay, to the left of 0, my function decreases as in x squared function, and between 0 and 2, the concave downward, so the decreasing pattern is similar to the negative x squared function. And then between 2 and 3, my function is decreasing, and but it is concave upward. So the graph looks like this. And then to the right of 3, my function increases. Okay, and to the right, concavity is concave upward. So the graph will increase similarly to that of x squared function. So it will increase like this. So this will be the shape of the graph based on the first derivative and the second derivative. So if I combine these factors, these facts, my graph can be improved. Previously, I had this one inside the red circle, just decreasing or increasing information can be considered. But if I combine the concavity, I can fine tune each decreasing or increasing portion. Right? So when you look at this graph, okay, so there are 2 inflection points and 1 local minimum, but there won't be local maximum. So this is the graph you can derive based on this first derivative and second derivative. So, as I said, by finding the points where f double prime is 0, which are 0 and 2, you split the interval into 3 pieces, and then you based on the sign of this f double prime, we could identify the concavity. And then, as I said, by combining the information, if you have the graphic calculator, TI-84, something like that, you can draw the graph if you have the calculator. But I can draw the graph myself without even without the calculator, because I can consider the information from the first derivative and the second derivative. So that's what we want to consider in this slide, curve sketching. So as an example, if I consider the following very complex function f of x defined by x to the 2/3 times 6 minus x to the 1/3. Okay, even if this function is complicated, I can find f prime and f double prime, and then I can find the points where f prime is 0 and f double prime is 0. Okay, and then I can perform some uh yeah, I mean the approach I used. Now, the problem here is this. F prime is 0 when this numerator is 0. Okay, but the problem with f prime occurs when the denominator becomes 0, right? So if x is 0, then x to the 1/3 will be 0. And f prime at that point is not defined. 6 minus x is 0 when 6 is 6, x is 6. And in that case, f prime is not defined either. So when your function is complicated like this, you need to find the points where f prime is 0 or does not exist. In other words, you need to find critical numbers. Please remember, critical numbers are points where f prime is 0 or f prime does not exist. And you need to split the interval with those critical numbers. So in case of f prime, the critical numbers are 0, 4, and 6. Okay, so this 0, 4, and 6, with these three critical numbers, the interval is split into 4 pieces. And then you need to identify the sign of f prime at those points. Okay, so based on this, your function first decreases up to 0, then increase up to 4, and then decrease again beyond this 4. That's what we can find. So probably you have a local minimum at 0 and local maximum at 4. So that's what we can guess. Okay, everything depends on some actual calculation. Now, if I have f double prime, I can combine some information from the concavity. And similarly to f prime, f double prime has -8 as the numerator, which is always negative. But the problem occurs when x is 0 or 6. Okay, so so okay, so we need to consider okay 2 points, 0 and 6, 0 and 6 for f double prime, and we consider these three reasons for f double. Now to the left, what is the sign of this f double prime? I have x to the 4/3 and 6 minus x to the 5/3. So to the left of 0, how can I tell the sign? If it is confusing, please pick up any point there. Usually some small value so that you can easily calculate the actual value of that expression. Say when x is negative 1, okay, what is the sign of this x to the 4 third times 6 minus x to the 5 third? And between 0 and 6, please choose any value. Say 1, you evaluate your f double prime there. Okay? And to the right of 6, choose any value there and evaluate f double prime. Okay? And f prime is the same. When you estimate this sign, if it is a little bit confusing, just choose any point in that interval. Okay, and then evaluate 4 minus x, x to the 1 third, 6 minus x to the 2 third. You evaluate your function there. Okay, so if you do that, you can easily tell that your function will be concave downward up to 0, to the left of 0, and to the right between 0 and 6. And then your function will be concave upward to the right of 6. So to the right of 6 concave upward, to the left of 6 concave downward. So by combining this concavity, I can fine tune the graph. So up to 0, the graph is decreasing, but since the concavity is concave downward, it will be decreasing like this. And then between 0 and 4, your function is increasing but concave downward, so it will be like this. And then between 4 and 6, your function is decreasing and concave downward, so like this. And then beyond the 6, your function will be decreasing but it is concave upward, so it is like this. Okay, so by combining this information, the concavity information, we have a better shape of the graph f, right? So this is how we draw, how we sketch the graph of the function. Okay? So f prime just gives the information about the increase or decrease of the function. Okay, but if I combine the concavity, okay, I can tune a little bit. So similarly to x squared function or negative x squared function. So this is how we draw or the graph of a function. These days you can use many calculators or some computer program to draw the graph of a function, but sometimes if your function, if your graph calculator or if your computer does not generate the graph, you can use this idea to find some certain pattern. Then this will help you identify the local maximum or local minima or inflection points. Local maximum and local minimum are important because the largest value on the whole domain or the smallest value on the whole domain can be found among the local minima, local maxima, and two endpoints of the function, and the function values at some critical numbers. I mean, the values where f prime does not exist, right? So please remember, you need to evaluate function values at critical numbers and endpoints. When I say critical numbers, we have two possibilities. F prime C is a 0 or F prime of C does not exist. You find such points and find the values of the function there. So if you get these critical numbers and if you evaluate your function values at two endpoints of the interval, among these, the largest value is the global maximum. Smallest values of these will be the global minimum, right? And that's what you want to find in many situations, in many real world problems, right? So, so identifying the local maxima or local minima are important. So, so if you want to find the local maxima or minima, you need to find, you need to evaluate your function at critical numbers, and if your function has f, if f prime is 0 there, then it is simple because you can differentiate one more time to get the second derivative, and then if depending on the sign of second derivative, you can identify, you can tell whether that is local maxima or minima. Anyway, anyway, so that's the end of this section, and let us consider the following section. Let us consider a few slides. Okay. And then we have a very strong rule called L'Hopital's rule. So this is very important. So in the midterm, I will definitely give some problems which use the L'Hopital's rule. So you should practice this L'Hopital's rule quite much. Okay, so please listen carefully in this section. Okay, now there are several two conditions where you can apply the L'Hopital's rule. So let us consider this f of x defined by log x over x minus 1, and I want to consider this limit. As x approaches 1, if I have just limit of log x as x approaches 1, it is simple because log function is a continuous function, so I can switch the limit and log function, and limit of x as x approaches 1 is just 1, and log 1 is 0. And if I have x minus 1, it is also simple because x minus 1 is a polynomial. And in case of a polynomial, if I have a limit, you can just evaluate this x minus 1 function there. So that means if I plug in 1 to x minus 1, you get 1 minus 1, which is 0. So if I have just one of these numerator or denominator, the problem is simple. The problem is complicated because if I have log x over x minus 1, the numerator is decreasing and denominator is decreasing to 0. So I don't know the answer. So in that case, we can have the L'Hopital's rule. So given two functions, f of x and gx, and suppose that I want to consider the limit as x approaches a, okay, f of x and gx, and if the first condition, if both f of x and gx are approaching 0 as x approaches a, then this limit can be obtained by considering limit of f prime of x over g prime of x as x approaches a. Okay, so this is the first condition, first situation. Okay, so if both numerator and denominator go to 0 as x approaches a, then limit of f of x over gx as x approaches a will be estimated by this one. So in the previous example, log x over x minus 1, in this problem, both the numerator and denominator go to 0 as x approaches 1. So in this case, what is the derivative of log x? 1 over x. What is the derivative of x minus 1? 1. You replace the limit with this one. Now 1 over x over 1 is just 1 over x. And in case of the 1 over x, this is a continuous function. So as x approaches 1, the value is 1. So this is the limit of the previous problem. Not 0, not 1, not infinity. Okay? In the textbook, we say such a shape is called an indeterminate form of type 0 over 0. You don't have to memorize this terminology. Okay? You need to memorize the shape, the condition. If you have this limit, and what is the condition? When both, not one, okay, both is a keyword, both fx and gx both go to 0, then this limit can be estimated by this expression. Okay, so previously we considered one example saying limit of sine theta over theta as theta goes to 0. Now as theta goes to 0, both sine theta and theta go to 0, right? Please note that, right? So in that case, I can replace this limit by the derivative of sine theta, which is cosine theta, over the derivative of theta, which is 1. And then you let theta go to 0. As the theta goes to 0, what is the cosine theta? What is the value of the cosine theta? It is cosine 0, which is 1. The denominator is already 1. So we get this value 1 as the limit of sine theta over theta as the theta goes to 0. That was the theorem formula we used the other day. And I could prove that using simple geometry, but I can check it using the L'Hopital's rule. Okay? So we considered the first type of the L'Hopital's rule today. And then we will continue. We will see some other special situation on Wednesday. Okay? And this is very important. So please listen carefully. And if you have any question, let me know. Okay? See you on Wednesday. Thank you for listening. Bye.